topography of the core-mantle boundary, and evidence are taken from numerical models. So the aims would be to firstly look at what happens to subducted material. Does it accumulate at the 670? And I mean, it's a zone between 650 to 670, and I'll refer to it as the 670 from now on. And to discuss what happens to this material. Does it avalanche once it accumulates? And essentially I've answered that question here, and now what happens to that material and its influence onto the topography of the core-mantle boundary. And tying everything together in terms of a global geodynamic system, what influence does avalanching have on tectonics at the surface? Just as an introductory slide of what I'll be talking about, the 670 transition is a mineral phase transition, and because of that mineral phase transition from, I think, spinel to perovskite and magma-wustite, plates are not readily penetrated through that zone. The core-mantle boundary, as we all know, is not a smooth boundary. It has elevations and depressions. The D double prime is a dynamic layer within the lower mantle. It's 200 to 250 kilometers thick, and it's believed to have a low viscosity and is able to flow readily, and where two large hot upwellings that we see today, below the South Pacific and below Africa, takes place. So the upper mantle, does the 670 transition represent a zone of accumulation of subducted material? Even though this paper is relatively old, the material in it is still viewed as correct today. Subducted material, in the model, they show that subducted material does accumulate at the 670, and this is done through seismic tomography imaging. And subducted plates, once they subduct, they accumulate at the 670 transition, forming dense pools of dense cold material. And interesting from their model is that they highlight from their spherical models that the relationship between the scale between subducted material and accumulated material is at a scale which is consistent with present-day subduction zones within the Earth. So there is a direct correlation between subduction and accumulation at the 670. So the core-mantle boundary topography, once this material subducts, how does it influence, once it avalanches, how does it influence the topography? And Masaki, in his modeling, shows that it does have a dynamic influence on the topography. Two things to consider from these models is that the D double prime is believed to have a low viscosity, and that subducted material that enters and avalanches through the 670 is considered dense. And the model shows that, I mean, the first model that they did is without consideration of a D double prime or avalanche material, essentially a control model. And what this shows is that the mantle does have a topography on its own without influence from anything else. And the topography is elevated and depressed. And two main elevations that we see today is below the South Pacific and Atlantic Africa, the two main hot upwellings areas that we see today. So without influence from that D double prime low viscosity zone, the mantle itself does have a topography. Now what influences this D double prime and avalanche material have on the topography is that when they include that D double prime layer, the topography is reduced by approximately half. And this is assumed to be the result of, because the material is able to flow, such fluid material does not readily stack up or form high altitude areas. And once they include avalanche material into the model together with the D double prime, they see that the core-mantle boundary is depressed below these cold downwelling regions. This is another image from another model in terms of isochemical modeling of the topography. And where you have cold downwelling, you have depressions in the topography and elevations near hot upwellings. These are two very important diagrams in terms of mantle topography. The first one is with that control model without the D double prime layer. And as you can see, the two hot upwelling regions, the pink to white areas, elevations in the topography, occur below the African plate, that's the African plate there, and the Pacific plate. Interesting in these diagrams is these black arrows which indicate horizontal mantle flow along this D double prime layer. And these arrows converge at these areas of upwellings and increased topography. Now this diagram shows when they include the D double prime and subducted material, and what you can see is that there is depressions along the core-mantle boundary topography, the core-mantle boundary, and these are associated with the subduction along the circum-Pacific. So elevations occur in hot upwellings and depressions along subduction zones and avalanching zones. So what we can take away from this is that the core-mantle boundary has a dynamic topography, and elevations occur in areas of hot upwellings due to the low viscosity D double prime layer. Dense or avalanche material causes depressions in the topography. And what we'll see later on is that, similar to this, is that what can be interpreted from the South Pacific region, the upwelling flow and increased topography, is that it is a response to downwelling near the subduction zones. If you add material in one place, you would cause elevation somewhere else. And the core-mantle boundary therefore has a dynamic topography which is influenced by subduction, avalanching, and mantle convection. Now, tying everything together in terms of a global geodynamic system, a tectonic reorganization model for the South Pacific is given, and Ishii and others, they propose that mantle avalanching drives the tectonic activities in the Southwest Pacific. I'll come back to this slide. What they say is that's a seismic tomography image of across the New Hebrides Arc and the trench, and it shows that subducting material off the Pacific plate, and it is actively avalanching. And they believe that their model shows that that avalanching of material has caused the reorganization from around 10 million years ago to the present of the trench. And their model shows that the trench has moved to the opposite side of the arc, opening the North Fiji Basin. And basically you can think about it as if you put your hand in a bath of water and you rapidly move it downwards, the surface of the water would be depressed and water would flow towards that areas of depression. And that downwelling of cold, dense material would have a gravitational influence on surface tectonics, and that's what they propose is happening. So to conclude, that the fate of subducted slabs is that because of their density and their viscosity, they build up and accumulate at the 670 and eventually avalanche towards the core-mantle boundary. And avalanching causes depressions of the topography, and together with the low viscosity D double prime causes elevations near hot upwellings, as we've seen, and avalanching could have an influence on surface tectonics. That's it.
Okay.
Questions?
I have a few questions. I'm just curious. You said the mantle has topography?
The core-mantle boundary.
The core-mantle boundary. And you said that topography is independent of anything else?
One of their models indicates that. That's just to show that on its own, without influence from anything else, it does have a topography. Now, what influence does outside material coming in have on that topography? Their model shows that.
Is there any information about any influences from the outer core onto the core-mantle boundary?
There is an influence because of the change from iron and nickel towards that silica-rich mantle. That's a chemical, that transition, I didn't look at in my model, and none of the models that I looked for core-mantle topography asked that question, because it's very difficult to include that sort of change at lower depths into the models.
I have one last question before Jason. One of the images you showed that some of the core-mantle boundary, one more, right there.
Yeah.
Had cool areas that were, I'm assuming this is pouring into the outer core, is that correct?
No, this essentially here, well, this would be the core-mantle boundary. This would be the core-mantle boundary here, and this is interpreted in terms of topography. This cold downwelling area is subduction and avalanching of material.
Okay, would any of this material during any type of subduction or avalanching occurring on and forming the topography of the TMB, would any of that affect anything within the outer core, or has it been suggested?
Not that I know of. Probably it is, but not in my presentation. I didn't look at that. Yes, Jason.
What kind of rates does the avalanching take place?
I figured someone would ask about that.
Yeah.
As you can see, well, from Ishii's models, they propose that the Pacific plate began subduction underneath the Australian plate around mid-Eocene times. And if you consider that to around 10 million years ago, where the accumulation began to avalanche, then you can see avalanching would take roughly in excess of 10 million years to go down to the core-mantle boundary. Now, there's no models that suggest, that I've looked at, that how long it will take to actually get to the CMB, but in terms of avalanching, it's in the order of 10 or so millimeters.
Depends on the volume and
Volume
mass
density.
of the performance of the 6 cm.
Yes, any questions from the professors?
Quite a few, but I don't think we've got time to do it. But only stimulated from the fact that you actually done yourself into the research. Pretty well. Thank you.
Yeah.
Right.